carbon dioxide, and it has a pronounced effect within first 2 decades of its presence in the atmosphere. In the recent international climate negotiations in Glasgow, abatement of methane emissions was identified as a major priority in attempts to curb global climate change quickly. Now, a team of researchers at MIT has come up with a promising approach to controlling methane emissions and removing it from the air using an inexpensive and abundant type of clay called zeolite. The findings are described in the journal ACS Environment AU. Although many people associate atmospheric methane with drilling and fracking for oil and natural gas, those sources only account for about 18% of global methane emissions. The vast majority of emitted methane comes from such sources as slash and burn agriculture, dairy farming, coal and ore mining, wetlands, and melting permafrost. A lot of the methane that comes into the atmosphere is from distributed and diffuse sources. So the researchers started to think about how they could take that out of the atmosphere. The answer the researchers found was something dirt cheap. In fact, a special kind of dirt or clay. They used zeolite clays, a material so inexpensive that it is currently used to make cat litter. Treating the zeolite with a small amount of copper makes the material very effective at absorbing methane from the air even at extremely low concentrations. The system is simple in concept, though much work remains on the engineering details. In their lab tests, tiny particles of the copper-enhanced zeolite material, similar to cat litter, were packed into a reaction tube which was then heated from the outside as the steam up gas, with methane levels ranging from just 2 parts per million up to 2% concentration flowed through the tube. That range covers everything that might exist in the atmosphere, down to sub-flammable levels that cannot be burnt or flared directly. The process has several advantages over other approaches to removing methane from air. Other methods tend to use expensive catalysts such as platinum or palladium, require high temperatures of at least 600 degrees Celsius, and tend to require complex cycling between methane-rich and oxygen-rich steams, making the devices both more complicated and more risky, as methane and oxygen are highly combustible on their own and in combination. The new process seems to have its peak effectiveness at about 300 degrees Celsius, which requires far less energy for heating than other methane capture processes. It also can work at concentrations of methane lower than other methods can address, even small fractions of 1%, which most methods cannot remove, and does so in air rather than pure oxygen, a major advantage for real-world deployment. The method converts the methane into carbon dioxide. That might sound like a bad thing, given the worldwide efforts to combat carbon dioxide emissions. But the researcher points out that carbon dioxide is much less impactful in the atmosphere than methane, which is about 80 times stronger as a greenhouse gas over the first 20 years and about 25 times stronger for the first century. This effect arises from the fact that methane turns into carbon dioxide naturally over time in the atmosphere. By accelerating that process, this method would drastically reduce the near-term climate impact, and even converting half of the atmosphere's methane to carbon dioxide would increase levels of the latter by less than 1 part per million, while saving about 16% of total radiative warming. The ideal location for such systems would be in places where there is a relatively concentrated source of methane, such as dairy barns and coal mines. These sources already tend to have powerful air handling systems in place, since a buildup of methane can be a fire, health, and explosion hazard. One potential major advantage of the new system is that the chemical process involved releases heat. By catalytically oxidizing the methane, in effect, the process is a flame-free form of combustion. If the methane concentration is about 0.5%, the heat released is greater than the heat used to get the process started, and this heat could be used to generate electricity.